So I'm going to discuss the photoelectric effect quantitatively. So as we discussed before that, every metal, it has a cutoff frequency for the electron to escape the metallic bond. Okay, so the minimum amount of energy needed for the electron to escape the metallic bond, I'm going to call it the work function. It's known as the work function. So the work function is equal to H times F naught. So the energy carried by the photon should at least be equal to this work function, which is hf naught, for the electron to be knocked off. So this phi, it's the work function. By definition, the work function, it's the lowest amount or the minimum. So this is the lowest energy needed for electron to escape the metallic bond. And why it's the lowest? Because I'm considering the electron to be on the surface. So if the electron is embedded inside, if it's embedded inside, then this electron will need an energy which is equal to the work function and a bit more. Okay, so that's why it's the lowest energy needed. Okay, now of course the unit of the work function in this case, if I'm taking H in joules, then it's going to be in joules as well. H, it's the Planck constant. And as you know that the Planck constant, it's equal to 6.63 times 10 to the power of minus 34 joules second. Okay. And F naught, it's the cutoff or the threshold frequency. So this threshold frequency, it's in hertz or in second minus 1. Now, if the energy which is incident by the photon, okay, if this energy incident by the photon is less than the work function, so the energy by the photon, if it's less than the work function, then this means that the electron will not escape. Okay, so E will not escape. While on the other hand, if this energy is equal to the work function, then the electron will just escape. So it will escape with a kinetic energy equal to 0. While if this energy of a photon is more than the work function, then the electron will escape and it will have a kinetic energy, so with kinetic energy. So I can write, by using all of these, I can write that the energy of a photon is equal to the energy needed for the electron to escape plus the kinetic energy. Now this kinetic energy, it's the maximum kinetic energy. And why? If I'm considering the electron at a surface. Because if it's not on the surface, then this kinetic energy is going to take a less value than this. Okay? Now, let me put, instead of the energy of a photon, I'm going to put as HF. So this is the energy carried by the photon. It's equal to HF naught plus the kinetic energy. So I can write the kinetic energy. I can write it as HF minus F naught. So I brought the work function to the other side and I have taken H as common. Or even you can write F in terms of C over lambda. So sometimes you are given the lambda, so you can directly substitute it into this equation. Okay, so this is the kinetic energy of the escaped electron. Now, let's discuss this using graphs. So if you look at this equation, which is this one, the kinetic energy, so this was the last equation that we have done. So it's HF minus HF naught. So if I want to find the kinetic energy of the electron which escaped, then all what I have to do is to vary this voltage. So this is a battery with a variable voltage. And as I increase the voltage of this battery, then the potential difference across these two plates is going to increase. And since this plate is a negatively charged plate because it's connected to the negative terminal of a cell, then this means that as the electron gets closer to this plate, this means that it's losing kinetic energy and it's gaining electrical potential energy. So if the electrical potential energy gained by the electron is equal to the kinetic energy of the electron, then this means that the this means that the electron will not be reaching this collecting plate, which means that this galvanometer is going to read 0. So in order to know what's the kinetic energy of this electron, all what I have to do is to increase the voltage of the collecting plate until it reaches a value where no more electrons are reaching this plate. Okay, which means that in this case, so when the galvanometer, so when G reads 0, so no more electrons are reaching, which means that the kinetic energy now is not sufficient to overcome this electrical potential difference. So this means that the kinetic energy lost by the electron is equal to the electrical potential energy gained by the electron. Okay, so I can write this kinetic energy in terms of the voltage or the potential difference. Okay, so now it's easy for me to measure the kinetic energy, and I can replace this in equation 1. Okay, so if I put instead of EK, EV, then, for example, I can plot instead of EV or instead of EK, I can plot so I can plot this on the y-axis and I can plot the frequency on the x-axis. Then I will have a straight line, okay, of slope h, so of slope equal to the Planck constant, and the intercept is going to be equal to hf naught, which means that it's equal to minus the work function. Okay, so this is the intercept. So this is the graph that I'm talking about here. So if you look at it, this is the graph that I'm dealing with. So if I'm plotting the voltage or the kinetic energy on the y-axis versus the frequency on the x-axis, then I will have a straight line such that the intercept is minus the work function. And this intercept on the x-axis, it's the cutoff frequency or the threshold frequency, which is f naught. Now, if I'm going to change the photo surface, so for another photo surface, you will notice that the line, if I'm going to plot the same thing, the lines are going to be parallel. And why is this? Because the slope is equal to constant. It's equal to the Planck constant. So since these two lines have the same slope, so they are going to be parallel. But what's different is the work function. So the photo surface 2 is going to have a higher work function than the photo surface 1. Okay, and you can tell this from the cutoff frequency. So here the cutoff frequency of photo surface 1 is less than the cutoff frequency of photo surface 2. Okay, I can as well, instead of plotting EV and or EK versus F, I can instead, so I can write this equation as following. I can divide both sides by E. So this equation can take this value. So this is the shape of the equation, phi over E. Then in this case, if I'm plotting V on the y-axis and F on the x-axis, then the slope in this case is going to be h over E, so the Planck constant over E. And the intercept is going to be phi over E. So the graph will look exactly the same thing, but the intercept and the slopes are going to be different. So if I'm plotting V in volts versus the frequency in hertz, so this one was in joules. Okay, so you have to pay attention for something. I have to mention something here, that this equation, it needs to be homogeneous, which means that here it's in joules. Okay, so here it should be in joules. So it should either all of it be in joules or all of it be in electron volts. So you have to pay attention to this. So in this case, the graph will look like this, where here the intercept, it's minus phi over E, And the intercept here, it's exactly the same. It's the cutoff frequency, but the slope here, it's equal to h over e. And if you choose a photosurface 1, which is of less frequency, so it will be exactly parallel to the first one, but the work function will be less and the cutoff frequency will be less. Now, let's talk about the same photosurface. So if I have exactly the same photosurface, okay, but what I'm doing is that I'm changing the intensity of light. So I'm emitting more light, okay? So this means that the current is going to increase. So look here. This is the same photosurface. And why it's the same photosurface? Because look, I'm emitting the same frequency of light. Since I'm emitting the same frequency of light, so this means that the kinetic energy is going to be the same, okay? But I'm increasing the intensity. And as you can see, the cutoff or the stopping voltage is the same. So since the stopping voltage is the same, so this means that the kinetic energy is the same, which means that I'm emitting a light of the same frequency but different intensity. Okay, so here light on same photosurface. Here the energy of light is the same, but intensity increases. So since the intensity increases, the number of emitted electrons will be more, but of same energy. So this means that the graph will be more steep than this one. So this is a lower intensity. Now, if on the same photosurface, I'm sending light of higher energy or of higher frequency, then as you can see, the emitted electron will be more energetic. So the stopping voltage will be more than if I'm sending green. So green has less energy. Okay, so the energy of photon incident here, okay, is less than in violet, which means that the kinetic energy here is going to be more, which means that the stopping voltage is going to be more. Okay. Now, if I, for example, if I decrease the voltage on the collecting plate here, so if I decrease the voltage on the collecting plate, or if I make it positive and increase it, then the graph will look something like this. So when the voltage is negative, at negative 0.4, minus 0.4, this is the cutoff, this is the stopping voltage. But as I make this voltage positive, you can see that the current is increasing because now the plate is attracting more electrons towards it. But of course, this will not be increasing forever. I will reach a point where the current is constant because all the electrons that are being emitted from the surface are reaching, okay? So since the same amount of, so the energy here is not changing, the energy is the same, and the intensity is the same, which means that the same amount or all the electrons that are being knocked off are reaching, so that's why I'm reaching saturation. So that's it for the photoelectric effect quantitatively, and that's it.